Hello and welcome to today's session. Today, we're exploring a powerful and efficient algorithm called binary search. This is a technique used to find a specific item in a sorted list quickly, and it's one of the most important tools in computer science. If this sounds new or intimidating, don't worry. I'm going to explain it step by step, starting from the very basics, using a real-life analogy to make it relatable. We'll also work through a problem with a visualizer to see it in action and discuss how efficient it is in terms of time and space. By the end, you'll feel confident understanding and applying binary search. Let's dive in. What is binary search? Let's start with the big picture. Binary search is a method for finding a specific item, called the target, in a sorted list of items. The key idea is that it works only on sorted lists, and instead of checking every item one by one, it repeatedly divides the search space in half, quickly narrowing down where the target might be. This makes it incredibly fast compared to looking through the list from start to end. Think of binary search as a smart way to guess the location of something by eliminating large chunks of possibilities with each step. It's like playing a guessing game where you get to ask questions that cut your options in half each time, leading you to the answer much faster than checking every possibility. To make this concept come alive, let's use a real-world analogy that you can picture easily. Real-world analogy, finding a word in a dictionary. Imagine you're trying to find the word mango in a dictionary. A dictionary is a sorted list of words, arranged alphabetically, which is perfect for binary search. If you were to search for mango by starting at the first page and checking every word one by one, it would take a long time, especially since a dictionary has thousands of words. Instead, you use a smarter approach. You open the dictionary roughly to the middle and land on a word starting with, say, kite. Since kite comes before mango alphabetically, you know mango must be in the second half of the dictionary because all words before kite are earlier in the alphabet. You've just eliminated the entire first half of the dictionary in one step. Now, you take the second half and open it to the middle, landing on a word like river. Since river comes after mango alphabetically, you know mango must be in the first half of this second half. In other words, between kite and river. You've eliminated another large chunk of the dictionary. You repeat this process, each time opening to the middle of the remaining section and deciding whether mango is before or after the middle word. With each step, you cut the number of pages you need to check in half. After just a few steps, you narrow it down to the page with mango. This is exactly how binary search works. It keeps dividing the sorted list in half, discarding the half where the target can't be, until it finds the target or determines it's not in the list. This halving process makes it incredibly efficient. How does binary search work? Let's break down the mechanics of binary search with a simple example. Suppose you have a sorted list of numbers 2, 5, 8, 12, 16, 23, 38, 56, 72, 91. This list has 10 numbers, and they're in increasing order. Your goal is to find the number 12 and 15 the targets, and report their positions in the list. First, let's solve it without binary search, using a linear search. Start at the first position, position 0, and check each number until you find the target or reach the end. For target 12, check position 0, which is 2. Not 12, move to position 1, which is 5. Not 12, move to position 2, which is 8. Not 12, move to position 3, which is 12. Found it. Report position 3. This took 4 steps, but in the worst case, target at the end or not in the list, you check all 10 numbers. For target 15, check each position 2, 5, 8, 12, 16, 23, 38, 56, 72, 91. None are 15, so after 10 steps, report that 15 isn't in the list. The time complexity is O of n, as you may need to check all n items. For n equals 1 million, this could take 1 million steps, which is slow. There's no way to skip items, and you can't use the fact that the list is sorted, so every search starts from scratch. Solving with binary search. Now, use binary search. The list is given. Let's find our target value, which is 12. Using iterative binary search to find 12. Searching at index 4. Going left. Searching at index 1. Going right. Searching at index 2. Going right. Searching at index 3. 12 is found at position 3. For target 15, as we can see, it is not present in the list, so the loop will exit once array ends with returning 0. Time and space complexity of binary search. Let's talk about why binary search is so efficient by examining its time and space complexity, which tell us how fast it runs and how much memory it uses. For time complexity, consider how binary search works. Each step divides the search space in half. If you start with a list of n items, the first step reduces it to n divided by 2 items, the next to n divided by 4, then n divided by 8, and so on. How many times can you divide n by 2 before you're left with just one item? This is the number of steps needed in the worst case. Mathematically, this is related to logarithms. The number of steps is the number of times you can divide n by 2, which is log base 2 of n. For example, if n is 16, you can divide by 2 4 times. 16 to 8, 8 to 4, 4 to 2, 2 to 1. So log base 2 of 16 is 4. 4n equals 1,000. Log base 2 of 1,000 is about 10, meaning it takes around 10 steps to find the target or determine it's not there. In efficiency terms, binary search takes O of log base 2 of n time in the worst case, because the number of steps grows logarithmically with the list size. This is incredibly fast compared to checking each item one by one, which takes O of n time. 4n equals 1,000. Linear search takes up to 1,000 steps, while binary search takes about 10. 4n equals 1 million. Binary search takes about 20 steps, while linear search could take 1 million. This logarithmic efficiency is what makes binary search so powerful. For space complexity, binary search is very lightweight. You only need a few variables to keep track of the search: the left boundary, the right boundary, and the middle position. These don't depend on the list size. You always use the same amount of extra memory, whether the list has 10 or 10 million items. This is called O of 1 space, meaning constant space, which is as efficient as it gets. Binary search's combination of O of log base 2 of n time and O of 1 space makes it ideal for searching large sorted lists when memory and speed are critical. General approach to binary search. To use binary search, ensure the list is sorted. Set 2 boundaries: left at the start, position 0, and right at the end, position n-1. While left is less than or equal to right, calculate the middle position as left plus right divided by 2, rounded down. Compare the middle value to the target. If they match, you found the target. If the target is less, set right to middle -1 to search the left half. If the target is greater, set left to middle +1 to search the right half. If left exceeds right, the target isn't in the list. This process works for any sorted list and any target, making binary search a versatile tool. When to use binary search. Binary search is perfect for finding an item in a sorted list, like looking up a number in a phone book or a record in a database. It's also used in problems where you need to find a boundary or threshold, like determining the smallest value that satisfies a condition, because the halving process can test values efficiently. You'll see it in challenges requiring fast searches or optimizations on sorted data. Common mistakes to avoid. Be careful to ensure the list is sorted, as binary search fails on unsorted lists. Watch for off-by-1 errors when calculating the middle position or updating boundaries. Use left plus right divided by 2, rounded down, and adjust left to middle +1 or right to middle -1 correctly. When the target isn't in the list, ensure you stop when left exceeds right, not earlier. Finally, don't use binary search when linear search is faster for very small lists, in less than 10, though this is rare. Conclusion. You've now mastered binary search. It's like flipping to the middle of a dictionary and having the pages each step to find a word quickly. We covered how it works by dividing the search space in half. It's O of log base 2 of n time and O of 1 space efficiency, and how it outperforms linear search's O of n time. The problem and visualizer showed how it narrows down the list in just a few steps, making it ideal for large sorted lists. Practice with different sorted lists and targets, or try problems where you search for values or boundaries. The more you use binary search, the more intuitive it will become. Thank you for joining me, and I look forward to exploring more algorithms with you in our next session.